up to clients and applications for use. The base network functions, that's something that we are finding is kind of foundational functions that a controller has to provide. Topology and inventory is kind of two basic functions that need to be provided for applications by any kind of a platform. But again, in a generic way, so that we can extend the functionality to any kind of network nodes that we find in the network today or will be finding in the future. Any questions so far on this? Yes?
So how do you decide whether you use the model-driven SAL with overflow or MD-SAL?
Right now, that's a good question. So the plugins and the applications have to be designed for one or the other. And that's what we will be talking about, how to design an application for the model-driven SAL today. Now, for OpenFlow specific, there is a switch that tells the controller whether to use the 1.0 AD-SAL based OpenFlow plugin or the 1.0, 1.3 MD-SAL based OpenFlow plugin. And that's the famous minus OF13 switch that you specify at the startup of the controller. It kind of decides which side is being used for OpenFlow. Yes? I would assume that the intent is to converge everything onto model-driven SAL for a variety of reasons, and some of which I will be talking about later in the presentation. Yes?
So if you have a mix of 1.3 and 1.0 OpenFlow, you could potentially have two disjointed.
The OpenFlow plugin on the right, the model-driven SAL one supports both. So
you have to explicitly specify to use that.
yes.
Well,
if you have applications that don't support that, there is the NSF adapters, and they can use the node boundaries APIs on the right side. So eventually, as the model-driven SAL and the plugins are more hardened, you would still have the adapters, and you would support the legacy quote-unquote APIs. Yes? No, okay. So you would support those. Yes. Yes, yes. Absolutely. So there is a REST API to the topology manager today, and there is a topology model, again, a proposed standard in IETF, where the topology is actually rendered from that model in real time by the RESTconf subsystem. So why do we actually why did we decide to go and design the MD-SAL? One of the primary requirements is really flexibility. So we've got to be able to run very different set of applications on the controller with very different APIs, very different functionalities. But we still want to have a common framework and a common programming model. So when you step back, actually the model-driven approach is not a bad way to enforce some commonalities through the code base. It also enforces or goes a certain way towards API governance and having consistent APIs for different kinds of applications. So basically specified models for your services or applications or protocols or plugins. And then have the APIs either generated in compile time or rendered at runtime from those models. There is a certain similarity and consistency to those generated and rendered APIs. Another advantage for the model-driven approach is we can have functionally equivalent APIs for different language bindings. So what we do today is we generate APIs from the model for Java, and we also render the functional equivalent REST APIs from the same model. So an application or a plugin that provides a model and is a provider of an API doesn't really know whether a client or a consumer of that API is coming through REST or coming through Java. It doesn't make a difference. Definition and the contract, the API contract is specified in the model, and then it can be translated into different languages or different interpretations. Another really important aspect is runtime extensibility. And this has two kind of components, or two aspects to it. One is we need to be able to augment the existing functionality, and the other is we need to be able to load new models and extend controllers functionality at runtime. So this becomes really interesting with protocols like netconf, which support uploading of models from devices that are discovered at runtime into the controller. And the controller can automatically adapt itself to the models that it discovers in the network. The same for plugins. You load a plugin at runtime into the controller. The plugin has a model or has a set of models in it, and the controller can automatically adapt itself to be able to work with the APIs that are created from that plugin, the plugin's model, and or interpret the data that the plugin needs or produces. Another really important aspect is avoid module and subsystem hotspots. It became relatively soon very clear that the API-driven SAL, it's a great idea. It's really at the core of the component of the controller, and remains at the SAL remains at the core of the controller. But in order to be able to provide kind of platform which can support different projects of very different nature, we have to avoid places in the controller code base or in a controller platform where when anybody wants to add functionality, they need to go in and add APIs or add some code into it. So the MD-SAL is designed as pure plumbing, where it connects producers and consumers, but it doesn't interpret the data in any other way. Or if it does have to interpret the data, the code is generated on time. That way, the development of different applications or different modules for the controller by different groups, different companies all around the world can happen independently of each other. There is no kind of integration, or the integration problem becomes a lot easier. I mean, there still needs to be integration, but people don't have to meet, don't have to kind of go and meet in the same piece of code in order to implement new functionality, which can be very diverging. And finally, performance and scale. And this also goes together really well with the common framework and programming model. The programming model and the APIs are generated from the models are designed for high performance. So absolutely use of asynchronous APIs, creation of immutable objects, just to name a couple. It may be a little bit of a learning curve to get used to it and start using those. But again, it enforces the same style and enforces uniformly programming for performance throughout the code base. Any questions about this? Okay. So how do we go and how do we compare the two different SALs? When you start on the left with the AD-SAL, it actually was performing two things, essentially two things. One was request routing, and the other was adaptation of APIs. So the request routing, it's if you have two different plugins that provide the same service, and a northbound plugin wants to talk to those southbound plugins, the SAL was doing the request. An example of this would be you've got a clustered controller, and different instances of the controller talk to different OpenFlow switches. An application wants to talk, wants to program a switch. It shouldn't really care about which instance goes and programs a switch. So the SAL should take care of it, and it was taking care of it, routing those requests. The other was adapting northbound service APIs onto southbound APIs. And again, there may be some code running in the SAL in order to provide that adaptation. So with the model-driven SAL, the request routing is preserved. but the adaptation has been taken out. It's yet another plugin. The APIs there's actually no northbound or southbound APIs. APIs are just generated from models, and both northbound and southbound plugins can use the same APIs if we just want to do request routing. If you want to do adaptation, then you define the northbound service model, and then it's an adaptation plugin that gets loaded into the controller. And again, the SAL is independent of that. The SAL can store a plugin's data, and it can do the routing, but it does not really interpret the data, and it's not dependent on any of the plugin's data or the models. So for the AD-SAL, the key services are request routing and service adaptation. For the MD-SAL, the key services are still request routing for both RPCs and notifications, and also data storage. So going a little bit into the modeling language that we use for the MD-SAL, it's Yang, and again, it's a IETF standard, RFC 6020. It's a relatively mature standard. It's been put out like 2-3 years ago. It kind of defines 3 basic constructs. It defines RPCs, it defines notifications, and defines data structures. So all 3 are then reflected in the function and the functional structure of the SAL. Any questions about this? So one thing that I'd like to mention, so Yang is a modeling language, but we also, in effect, use it as an IDL, interface definition language. And in order to support the function of the controller, we had to do a couple of minor extensions, specifically around augmentation and around being able to put together a network view, which we call network mount, put together a network view stitched together from different submodels that can be provided by different components or different network devices. The key kind of architectural tenet of MD-SAL is because the models are loaded at runtime and they're bound to APIs and to code at runtime. It's dynamic late binding. And also, we've got generation of code from models both at runtime and at compile time. And Tony and Robert can go into more details about how that happens during the later part of the presentation. So how do we create a view of the network? Yang and Netcom, the standards provide kind of one tree for a subsystem, a server, and it's divided into operational and config spaces. And we kept that, that principle, that notion, but extended it to the network. So you still have 2 subtrees, topology, operational and configuration. Some of the subtrees can actually be mirrored both in the configuration and operational. So imagine you have a node, like a switch or a router. It has both configuration and operational states, but you've got things like topology that's only operational state. And the tree is stitched together in real time from different components by different providers. So, for example, the topology is provided in this example by BGPLS. So it creates and puts into the tree different subtrees. The topology exporter for BGPLS provides actually 3 kind of major subtrees for BGP v4 prefixes, v6 prefixes, and BGPLS, which is actually link state topology exported through BGP. A similar topology can be exported into and put into the tree by an OpenFlow topology exporter. Then you've got things like OpenFlow nodes. They are put into the network tree by a flow-capable inventory node. Statistics for those flow-capable nodes are put into the tree by the statistics manager. But other trees can be put into the, other nodes can be put into the tree by other components, such as netconf. So we can have a mix of OpenFlow and netconf capable nodes in the same network view. And it's not shown here, but you can have things like SNMP or CLI protocols and nodes as they are discovered and can be managed by those protocols will also be put into the inventory tree by their respective protocol components or directly by plugins, such as here in the netconf plugin. I mean, the netconf plugin discovers the node and discovers the model in the node, and then injects the node into the network tree. Yes?
If the node has entities, of course, that are both netconf discoverable and OpenFlow capable,
It would actually right now go into two different places, yes, and it would be visible through two different subtrees. Now, it becomes a really interesting question, and this is what we will have to somehow solve probably as a community, and maybe even with standards bodies, is how can we associate and figure out that the different nodes in the different subtrees are actually the same node. So some kind of a universal node identifier would be a really useful thing if the industry can agree on that. Right now, there is nothing like that. So you kind of need to know which nodes are which and how they may be related. Okay, so again, the mechanisms depend on the protocols. For OpenFlow, the switches connect to the controller, and as they connect to the controller, they appear in the inventory. For netconf, what we have there right now is you have to configure the remote netconf server addresses so that netconf can go and connect to those different remote nodes. And then inject those nodes into the inventory. But you can also plug in, and I would assume this would be an application going forward. You have any kind of a discovery mechanism, either PMP-based or the netconf reverse SSH, which will be similar to what OpenFlow is doing today, where actually the nodes call home. And connect to a controller. Or any kind of a discovery mechanism can be running as an application in a controller, can be populating the inventory database as well, and then telling the individual protocol components to go connect to those nodes. So it's a really good question, and it's an unsolved problem today. I mean, we've got the configuration because that's all that we could do in the time that was left. Okay, so when all the pictures of the controller that you have that are actually more or less network view of the controller. You've got kind of the protocol plugins at the bottom, you've got service plugins at the top, and then you've got the adaptation in the middle. But what it actually is, when you look at it, you've got the SAL at the bottom, which is kind of a backbone of the system. And then the plugins plug into the SAL, into the backbone. And the SAL doesn't really care whether the plugin is a service plugin or a protocol plugin. The SAL is a plumbing that connects consumers and providers. And it doesn't care whether the consumer is a protocol plugin or a service plugin. So it really is an infrastructure service that is independent. So you kind of fold the protocol, the controller, and have the backbone, which is the SAL, and then you have things that extend the controller, be it talking towards the network or talking towards applications that plug into that backbone. Now the nice thing about looking at it this way is you can actually implement clustering in addition to those layers that we talked about and that you see in the architecture presentations. Clustering is kind of yet another layer where in order to implement the primitives that we talked about for the SAL, notifications, RPCs, and data store, we need to have two clustering mechanisms that will be facilitating communication of different containers. One is a message bus that will be routing RPCs and notifications, and the other is a shared data store that where the data and different portions of the tree can be stored and shared between different instances. Now, going forward, I would like to invite Tony and Robert to show how to actually build an application and walk you through a code of an example application that we prepared. Before that, though, any questions about the general architecture and the principles? Yes. Load balancing is a function that is almost like a policy kind of on top. So the message bus and the data store are really just plumbing mechanisms. And then what you could have and should have is mechanisms that monitor the load on different instances and then decide where a particular request should be routed. So look at the message bus and the data store almost like a forwarding table, whereas the load balancer would be a routing table which populates the forwarding tables, basically deciding where things go. No, I have to use your laptop. For slides, we can use my laptop, but it's actually better. You don't have the slides. Okay. So why don't you continue with the slides and then we switch to your laptop for the demo.
So basically, what Jan mentioned before is that we have at the core there are the Yang models, which defines the data structures, RPCs, and notifications. These are the input, and when you are building the plugins or applications for the controller, and you are defining your new model, we provide you with the required tooling for that. Basically, we have in the Yang tools project. We have the set of tools which takes the Yang model and generates in the compile time with the Maven plugin, generates for you Java interfaces, which represents the RPCs, the data structures, and so on. So you have nice APIs. As a normal Java developer, Java APIs, nothing funky there. This compiles into the jar file, which describes the model. In the runtime, this jar file also contains the Yang model, and basically in the runtime, this is used for the other functions provided by the MD-SAL. And for the plugin development, basically you are developing your plugin against these generated APIs and against a set of MD-SAL APIs, where basically like a registration of your services and so on. Also compile it with the Maven, and in the output you get a jar, which you need to deploy to the controller, and that's all to have your application running.
So the clustering is working today on the MD-SAL approach, but MD-SAL is not operational yet.
Currently, the clustering support for the MD-SAL isn't in the Hydrogen currently. Okay. So as the demo application, we took the learning switch example, which is available on the SDN hub, and we ported this example and created it for the MD-SAL. Basically, the functionality is it listens on the packet ints. When the packet int comes up, it extracts the MAC address, keeps the mapping between the port and MAC address, and then if it has all enough information for creating a bridge flow, it configures the flow via MD-SAL, via data store and MD-SAL, and otherwise it acts as a hub. So basically, the learning switch application is built on top of the MD-SAL. It interacts with the models for the flow-capable node, such as a packet in notification and the RPC transmit packet, which is the packet out, and uses the data store for the configuring the flows. And there is a forwarding rules manager, which actually manages these changes in the data store and translates them to the flow mode messages for the OpenFlow plugin. So the workflow is basically the switch sends a packet in. This gets translated by the OpenFlow Java library into the packet in message from the binary stream. Then the plugin sends this to the MD-SAL as a notification. The learning switch itself registered as a listener for the packet in notifications to the MD-SAL, so it got delivered the notification. And basically, that's the first packet in. So now the learning switch invokes the transmit RPC, transmit packet RPC, which MD-SAL routes to the correct OpenFlow to the OpenFlow plugin or to the OpenFlow plugin, which then basically uses the OpenFlow Java to write it down to the output stream and sends to the switch switch. There is as I mentioned before, and also we have the flow-capable node model, which actually adds the configuration options for the flows and tables. So now when the switch, now the other part, when the switch has all the information, it actually writes to the data store via MD-SAL APIs, writes the new flow, which should be put to the switch. The forwarding rules manager picks that up and basically sends the RPC add flow or remove flow, add flow RPC that got routed to the OpenFlow plugin, sent down to the switch as a flow mode message. And also, basically, as Tian mentioned before, the RESTconf works directly with the MD-SAL. So all these flows which were installed by the learning switch are also visible via the RESTconf. So we could look into the configuration space for the flows, and you will see that flows there. So for building the sample application, we have the prerequisites, which is Java 7, which is required for the running the controller, maybe Maven 3.05, Linux or Mac. Also Mininet, which supports the OpenFlow 1.3 or CPQD, and the OpenDaylight base edition. Okay, I think we could switch to the demo. Here. Let me configure this better. Does it support? Oh, it doesn't. So let's go with this. Just a sec. Okay.
How would you negotiate that the plugin is, the VSTP plugin is not there, but there is some other plugin available to provide the same service as the VSTP?
Could you speak up, please?
The service abstraction layer is, I'll go at least on bundles and how OSJ works. OSJ provides a service registry. Multiple providers can come and register themselves when they come up. So OSDB is one plugin will come and say, you know what, I support configuring service.
Aren't we getting the?
Overflow, on the other hand, never say I suppose data file service.
Okay. I was just confused. So okay.
So when the plugins come up, when the registry what they're capable of.
This is really weird.
SAL knows these plugins are what, and expects the same thing to the up not to the.
Okay. So basically, to develop the application for the. From where is this going? Okay, so basically to develop the applications, we need Maven, Eclipse, and OpenDaylight-based distribution. This application, the sample application is submitted as a patch to the OpenFlow plugin, so it will be available in the OpenFlow plugin repository. And basically, for the dependencies to write this application against the flow-capable model, you need to be compiled against some core models, which is actually, you could see we have using the inventory model, which describes the base inventory. Then we have the model for the flow services and some baseline model for the OpenFlow, which defines or for the flow-capable nodes, which defines base terms, what as a group, flow, meter, and so on. And also the MD-SAL APIs. So basically, the operational mode of that sample application is we are listening on the. So the first thing we need to start our application. Basically, we did that by. We did that by extending the binding aware consumer, which is some helper class, which takes care of waiting till the MD-SAL is started, and then calls the callback, which is that you have this session with the MD-SAL, so you are able to communicate with the MD-SAL as a consumer. Basically, you are not exposing any model, any APIs, you are just consuming the existing ones. And we are setting, from the context, we are getting our dependencies, which we needed. The one is the data broker. Basically, that was which provides us access to the overall data tree, which Jan mentioned. And we are using it to configure the flows and read for example, look up into the operational subtree to find out the OpenFlow nodes which are running and what tables there are. The other one service we need is the RPC service, which is the packet processing service. We are using it to send the packets out. And the third one is basically the notification service, which we are using to subscribe for the notifications. Okay. And we have the other, okay?
What if those services are not available?
How do you mean, what if they are not available?
I mean, the packet processing may not be available. Maybe coming later.
The packet processing service is this. You are getting the MD-SAL version of that. That is always available when you request it. What happens is, and actually that could happen, there could be no provider which actually provides the packet services for the switch you are requesting. So you always get the service, but there could be no provider which actually provides that implementation for that particular switch.
So, I mean, how do you react in that conditions?
Could you repeat your question?
Yeah. If there is no implementation for that packet processing,
There is always implementation for the packet processing service. There is no consumer, no provider which exposes itself as a packet processing service for a particular device. There is always still one implementation present in the MD-SAL. Basically, what does the MD-SAL, and this goes to the MD-SAL internals, is for each service instantiated 2 implementations. The one is a proxy, the second one is a routing, the routing instance. And the routing instance takes care to route it to the particular, for example, in the OpenFlow models, to particular plugin which processes that node. And if we go into the details, basically with the clustering, the instance could be, in the future, could be running in different container. So there is always still one instance, which could fail if there are no implementation for if there is no switch processing the node you are trying to send a message. Any other questions?
if there is no provider at all, just the MD-SAL, then when you make a call to that API, what do you get back? Just null?
You will get back the illegal state exception. There is no provider for that. So we are getting the packet processing service. And we start the learning switch manager. The learning switch manager is a class which basically, when it started, initialized small helper class, which is also part of this demo, which takes care of writing the data to the MD-SAL, writing the flows which are to be programmed. Also, it has a small helper utility, which is packet in dispatcher, which basically looks into packet in and selects the instance of the learning switch based on the for which node it was instantiated. And there is a multiple learning switch handler. Basically, we have one instance of the learning switch per one device. So it maintains the flows for that device. And we have also so basically these are the smart worker classes. And then basically, for example, we have the packet in dispatcher, which is the listener for the packet ints. If you look at that class, it implements the packet processing listener, which has a callback on packet received. So basically, the learning switch manager registers itself as a listener. This packet in dispatcher is registered in the MD-SAL as a listener for the notifications. And when the packet in notification occurs in the MD-SAL, it's delivered to the packet in dispatcher. And also, we are registering the second listener. This is a special one. This is the listener which listens on the changes in the operational data tree. And actually, this listens in the data tree for the paths nodes, so we are getting to the inventory. It listens on the subnode node, which represents one node. And basically, it listens on the extensions, with the extensions of the node for the flow-capable node. And it listens on the table. So basically, this listener gets always notified if the some OpenFlow table is discovered or created in the operational data store or changed. And that's the startup. So this listener is really critical because in the OpenFlow 1.3, basically, when you want to program a flow, you need to have a table. So basically, this listener is always invoked if the new switch is populated to the inventory, or the new table is populated to the inventory, And it looks up in this simple demo for the table with the number 0. And if it had the table number 0, it will create the learning switch for that table, for that OpenFlow switch.
Just in the context of trying to, those of us trying to understand MD-SAL better, if, and maybe this will be covered later, but if you could maybe touch on which parts of this, which skeleton code gets generated, say, from the model, versus obviously lots of some implementation that's been done.
Okay, basically that whole demo is handwritten. What was generated from the model is all this OpenFlow, all these 1.3 specific APIs and API definitions. And if we look into it, model flow base, it's this huge list of classes which describes every aspect of the OpenFlow 1.3. Basically, all the actions, all the match fields, for example, the flow. Here we have the flow definition. And I don't have the Javadoc sources, but basically, all the API contracts, all the data, all the transfer objects for the data structures, all the small pieces which you are using to communicate with the other components in the system, that's for the compile time. In the runtime, what we are generating from that is actually the implementation of the request routing for the MD-SAL. So that the implementation is runtime generated class, so it's always efficient, and the REST APIs. So basically, okay, we are listening. So let's go back to the demo. So basically, we are listening on the tables. If we gather the table, and the table has the ID 0, which will be used for the demo, we are spanning a new switch. So here, basically, these facades take care. When there is a table, we are shortening the table because table is in the form in the tree. As I mentioned, the table is underneath the node. So we are shortening the path to get the ID and the location of the node in the overall data tree. And we are using that as our identifier for the node. So we are spanning the, so we shorted that. If we don't have already instantiated the learning switch for that node, we are creating a new instance. And now we have the instance of the learning switch for particular switch, which is there, which connected to the controller. That's the first part of it. The second is basically the implementation of the learning switch. As I mentioned, the learning switch listens on the packeting notifications. So basically, if it is learning mode, if it isn't in learning mode, it will ignore packet. Basically, it gets the packet receive notification. This notification contains a path to the port on which it was on which the notification occurred. So we are just checking that the notification we are processing is for the node connector, which is in the overall data tree underneath our node. Otherwise, we are not processing that packet. Then from the packet, we are extracting the MAC addresses. We are getting the interface ID. And here, only for debugging purposes, we are getting the interface ID from that path on which the notification occurred. And basically, then we are updating our internal structure where we are mapping the MAC address to the port. And if we get, if we also have the destination, we have port for the destination. Basically, we are adding the flows to we are adding flows to the data tree, so it's a normally configured flow. It's not side-loaded. Every application which is able to read the data tree is aware of that flow. And to add a flow, basically, we are creating a path for that flow where it should be written, which is basically the instance identifier. And the instance identifier is a really core concept for operating on the data tree. Instance identifier actually describes exact location in the data tree. The one thing which we did for that, if you have a model and you are using the instance identifier builders, we are at the compile time, we are making sure you are not writing you are writing at the correct place in the data tree. So basically, for example, to create an instance identifier for the flow, basically here we take the instance identifier for the table because the flows are located in the table, and we are appending a child that we are going into the flow, and the flow with this key we are using to build the immutable instance for the DTO is also derived from the Yang. So basically, we are starting building a new flow builder, setting table ID, name. Then we are creating Ethernet match, setting the Ethernet source to the source MAC, destination to the destination MAC. Then we are creating the output action. And then we are dealing with the OpenFlow 1.3, so we need to create the apply actions instruction. We need to put that action into the apply actions instruction. And then we are basically building the rest of the flow and returning it to the code. And now comes another aspect. Basically, we are writing that to the data tree. Any write to the data tree actually results in is a two-phase commit. So basically, it could be successful or unsuccessful. And here, basically, we are starting the transaction, how to write this flow to the to the data. We are on this path into the overall data tree. We are writing the body, that flow. Actually, that transaction, the forwarding rules manager is registered itself into the MD-SAL as a two-phase commit handler for that particular flow subtree. So it validates that flow, and when everyone who is registered to validate that subtree accept the input, the forwarding rules manager will program the flow to the OpenFlow plugin, send the RPC to the OpenFlow plugin, and the OpenFlow plugin will send it down to the OpenFlow switch.
Quick question. Do you get kind of a final confirmation that the flow actually was programmed correctly, or does it get accepted?
Okay, so basically, if you are doing this in the transaction way, for each transaction, you have a transaction status. So basically, you could, also this commit is asynchronous, so we could wait on it. And basically, you can read the transaction status if this transaction was successful or unsuccessful. Go ahead.
The transaction is a data transaction, though, not a transaction down on the device. So what happens if your data transaction action succeeds, but the callback down to the flow manager pushing down the device fails? How is the API notified of that?
That's the implementation detail of the forwarding rules manager. Actually, the FRM uses that contract to program the flows down, but in that case, that flow is only known to the OpenFlow plugin and the switch. So we are using the data store, so the other applications are aware of our flows we are trying to program. So, and not pushing something sideloading via the RPCs directly to the switch, and the only way how to discover that switch is to do the statistics collection. Okay. Okay. In current implementation of the MD-SAL, this is stored in the hashmap data store, which is internal to the MD-SAL. We have the cluster data store implementation also for that. So this flow is always stored in the data store. And for example, via REST-conf, when you are reading the flows via REST-conf, you are not going directly to the forwarding rules manager. You go to the well-known location in the data store, because we are using the models, so everyone is aware of these well-known locations where the flows are. So the REST-conf reads directly from the data store the data. And actually, it's only implementation of the forwarding rules manager that it listens on the transactions. And when the transaction succeeded, it does the flow programming via the OpenFlow plugin. Yeah, it's yeah. Basically, it's operational for the run.
But it can be backed by a data store, but it should be able to specify different policies for the persistence. And you can imagine actually having different policies for different parts of the subtree. So some parts may be persisted, some may be not. We also have actually two subgroups. They're one is operational, one is configuration.
Go ahead. Could you repeat your question a bit louder?
The resources on the core, can be shared in the plugins or not?
The resources.
For example, I'm not sure if you have other, like some resource like data worker.
Oh yeah, these resources could be shared. Actually, they are shared across all the MD-SAL aware plugins in the controller. And also the resources which are stored into the data store could be shared. Basically, for example, the topology model itself is defined that there are multiple topologies. And for example, there are multiple topology exporters which writes that model. So basically, there is OpenFlow LLDP topology exporter, which does the LLDP discovery and exports the topology. For the OpenFlow, there is a BGP-LS topology exporter, which actually uses the BGP, uses the BGP listener to listen on the BGP-LS protocol, and exports the topology based on that into data store. So also the data store is shared resource. The synchronization in what sense? Could you repeat that? Concurrent modifications and okay, so these transactions, basically there is a two-phase commit, and your commit could fail because the predicates for your commit, for example, you were writing to some place and someone already succeeded to write to that. Basically, your two-phase commit will fail. we are doing everything in a transaction, and these transactions could fail for you. And you could listen to your access to the data store to figure out that, okay, you failed because, for example, you didn't pass the verification, validation, or basically that the resource changed before your code was executed.
So we show that the future you get is listenable, so you can usually attach to that. And once that commit succeeds or fails, you get a specific notification callback, and you can examine whether the effects took place or canceled or whatever.
Any other questions, or should we continue basically to compiling and running the demo application? Okay. So let's go here. So okay, as I mentioned, the application is inside the OpenFlow plugin project for now. So let's go to the OpenFlow plugin. Let's go to the samples folder, to the learning switch. Basically, to compile from the command line, you need to only run the maven clean install. Okay, our example application gets compiled. The source is basically in the target folder. The jar for that is in the target folder, which is the learning switch 003 snapshot. So let's go to start running the controller and install it. Okay. I have the distribution. I have downloaded the official distribution of the base controller. So let's unzip it. Okay. The next step is, let's go to the distribution. There is already one learning switch example in the distribution, so we are going to remove it. So we will make sure that only ours is running. Or it was a simple, okay. And let's copy ours here. Samples, learning switch, target. Okay, so basically in current distribution we have also the MD-SAL there, and we have the adapters which converts from the OpenFlow 1.3 plugin and MD-SAL to the MD-SAL. So basically you will have two learning switches running concurrently.
So you'll have double entries in the...
Yeah, double entries and unspecified behavior. Where the one writes the data via MD-SAL, the second one writes the data directly to the plugin. So okay, we copy the jar into the controller, and let's run the controller. That's the with OpenFlow 1.3. Okay, we started the controller. It will take some time. Okay, Mininet is turned off. In the meantime, what I forgot to mention is actually in order to receive the packet ints in the OpenFlow 1.3, you need also install the default flow, which will actually forward the packets to the controller. So that's the first operation, which is the learning switch doing. If we got the table and we know that we are connected to the switch, we will install the first flow, which matches everything, has the lowest priority, and forwards all the packets to the controller. And okay, so we started the controller. Okay, let's start the mininet. We will start the mininet with a single switch and 10 hosts, and OpenFlow 1.3 plugin. OpenFlow 1.3 OVS. So this is adding the controllers. You could see the controller get an incoming connection from that. And if we go to the REST-conf, to the REST APIs of the controller, and if we look at the operational inventory, that's the model we mentioned. Let's make this smaller. We get the operational inventory, which has a path in the form basically similar to the Java APIs. Basically, we are requesting the OpenDaylight inventory model and the nodes underneath. We can see we have the one node, which is OpenWeb switch, has ID of 1 and has a maximum and its capabilities. And if we go deep down and we look at the configuration for that node now, basically we could see that in the table 0, we constructed the URL for the table 0, which is OpenFlow nodes node, OpenFlow 1 node, and we are getting the state for the table 0. We can see there is one flow which has the name of the all packets to the controller, which is programmed by our application, has an instruction, one instruction which is output to the controller, has a priority 0, is installed in the table 0. So now let's go to the mininet. If we start pinging, for example, from host 1 to the host 2, we get the ping working. And if we look at that table again, and let's change this, and we get the table again, we could observe that there is additional flow, which is basically matching on one MAC address on the source destination and outputs it to the correct connector. And if we do a ping all here, okay, 0 packet dropped. We could observe here now. Okay. We could observe now that we have a flow for each combination of the hosts installed into the MD-SAL data store and also provisioned to the switch. And if we look into the operational state for that table, which is basically statistics collection, basically we just need to change the config in the URL to read to the operational. This is collected by the statistics manager written for the MD-SAL. You could see basically all the flows and statistics for that how many bytes were matched by each flow we programmed down. And for example, if we run the another ping flow, ping all, now this number currently it's 35 kilobytes, which were processed by the table. It takes some time. Actually, the statistics gathering runs each 5 seconds or 10 seconds? 10? So let's try now. We can see actually that the packet count went up. So basically these flows which we installed in the table 0 match the pings, and basically were used with the pings and not sent via packet in. And the counters were increased for the flows. Any questions?
So are you planning to continue the AD-SAL and MD-SAL representing the feature,
Good question, but that's much more for the discussion for the whole community, not only us.
So maintaining the synchronization, obviously somebody's work. For now, we are still establishing that. It really depends on how many APIs get defined where. But I think that at some point, we will need to move onto MD-SAL simply because the sheer amount of APIs need to be defined will overwhelm whoever is at central API authority. That will need to be distributed.
So independent of whether you move both of them forward, I assume it should be possible to create a addition that just bundles MD-SAL and not AD-SAL.
Yes. Yes, it is possible to create the MD-SAL only distribution.
But that's not a standard distribution with the hydrogen.
No, that's not standard distribution.
whatever you like, it's better than fact. This is nothing more than electric system. So what happens is that this one is just one thing that is being provided. But the development, choose and make your own. That's pretty much the idea. You should not be religiously looking at the OpenDaylight distribution. That's just the same. That's the idea.
Topology is, see, some of the innocent functions have actually been taken or superseded by the inventory manager and the topology manager. Topology is more. But for the legacy APIs, with the adapters, they would be maintained no matter what. So yeah, but you're right. I mean, not all of them will be implemented because. Right. Yes, exactly. And certainly.
Yeah, but maybe you don't need it for the whole steps. That's fine. So if you choose the whole distribution, as you will, and basically in this case, that's I guess that's the proper way of doing it. Just use this distribution as a blueprint that you can look at that. You are free to create as much as you want. That should be one of these.
Any other questions? Okay. So basically, there was a question regarding the what is generated. So, for example, to describe the whole OpenFlow protocol, and the 1.3 protocol is really more complicated than 1.0. You had to define a lot of APIs. The current API contract for the model-driven SAL for these protocols is described in, I think it is described in, the basic concepts are described in the in the 8 files. For example, if you look at the match types, basically here is the model, Yang model, for all the match types which are defined by the specification. In case of the API definition, you basically are required to write a class or to write a code for each one of these definitions and implement a lot of getters, setters around it. And basically with the model-driven SAL for that one, we are generating, and that's what Jan also mentions, that we are enforcing some API contracts. We are generating, that was the match types. Let's go here. Basically, we are generating the classes, the interfaces, and if it is a concrete TO, we are also generating the builder. I don't have the sources attached. Yeah. We are generating the builders, and also we are generating the immutable implementation. So basically, any object which comes out of the builder is immutable, so you don't need to do the copy. You could pass it to anyone. Nobody will change it. So we are doing this safe. We have this safe contracts for multi-threading when you are passing the objects. You cannot pass to the MD-SAL the builder. You can only pass the you couldn't pass only the product of the builder, which is immutable. So once you send the data out to the other component, that object is still one instance, but nobody can change its internal state. So you don't need to lock on that, for example. There's one of the API contracts we are able to enforce with that all the objects which are traversing between the components are immutable. Also, this generated interfaces contains a lot of small, I can show it, contains a lot of marker interfaces and a lot of additional metadata, which, for example, we are using in, as I mentioned before, in the instance identifier, which is the path in the data tree. So, for example, as I mentioned, the structure defined in the model is that in the inventory you have a top-level container which is nodes. Underneath you have a list of the node. So you have several nodes, and then that's the baseline inventory. Then there is the OpenFlow inventory, which contains the augmentation, for the flow-capable node. So if we want to get the data for the flow-capable node, basically the path will be, you want to get the extension, which is a flow-capable node class. And actually, this type safety goes to the point that, for example, when you are trying to request, let's say, flow node, something different. For example, you are trying to reach some flow node. This is not augmentation or not extension of the node, so basically you get a compile time warning, even if you are trying to build a path into a data store. The same goes, for example, The hierarchy goes that in the node, we have the node connectors. And we don't have the another nesting of the node. So basically, for example, if you go here and try to nest the path once more time, you get a compile time warning. So it's really hard with these data store APIs and with this instance identifier to make mistake when you are reading from the model-driven data store. And you are constructing the paths. So when I write a node connector here, now I don't get the compile warning because the node connector is a child of the node. So for example, these are, and based on that we have the model, and we can enforce a lot of marker interfaces during the code generation and a lot of helper information. We are able to build a more safer APIs for the Java coders. And also, what Jan mentioned before, basically, if we go to the RESTconf, and you see that class that we have, that path starts with the nodes, which is from the OpenDaylight inventory model. We go to the node, which is a node. We are providing it with the ID. If we go to the RESTconf, and you want to read the state of the node, it's really same. In the body you have nodes, node, ID, okay, here. And you are able to read the state of the node. And same goes for a table. Table is basically contains the augmentation and just adds a table keyword and key. So reading the table 0 for that node is in the from the REST APIs is really the same. And if you issue a put on the REST APIs, it triggers the same two-phase commit transactions as we are invoking from the code. So the forwarding rules manager doesn't have to expose any specific APIs for the, for example, for the RESTconf, for the Java APIs, or other binding will we add, because the MD-SAL takes care that it translates it to its bindings and could participate. And that's the API convergence Jan mentioned, that we are providing similar APIs, we are just changing the language binding. Also just, let's switch to the XML. And also on the wiki, you will find on the wiki for the OpenFlow plugin and OpenDaylight, there are examples how to push the flow via RESTconf. And for the programmers and that from the application developers and plugin developers, they are not programming against the RESTconf. They are programming against the MD-SAL. And the thing which is, MD-SAL knows how to translate the RESTconf into the Java. So they are called as if they were invoked from the Java application. So that's one of the strengths of the model-driven architecture. Basically, you have one set of APIs against you are compiling, and from the models we could derive the other sets and other bindings for someone else. And we also know how to translate their calls into yours, from one language to the another. Any other questions?
Is it possible to write applications that extend the model?
Yes. Basically, that's what actually happened. We have the really simple model for the inventory. And if you looked into the inventory model, okay, this will take, we don't have the sources for that, so let's look into the release chart. The inventory model is really one of the simplest one. The inventory model is really simple. Basically, it defines some primitives and defines a structure. As I mentioned, there is a top-level container, which is nodes. There is a list of the node. And we are using here a reference for the node. And each node basically contains a list of the node connectors. That's all to the inventory model. But if you saw, what I was demonstrating is basically we were writing in the inventory, and here, for example, here we are getting from the inventory. Just let me copy this. We are getting from the inventory. Basically, you could see we are going into the OpenDaylight inventory. We are going to the nodes node. We are going to the OpenFlow1 node, and we are going to the table. In the original model, there is a node table. So there is another model, and this model is.
So you hit the URL. You saw OpenFlow $1. It really says the name of the model. That actually defines that
Robert, that is not the name of the node.
it's not the node, it's the name of the model.
That here, this is the name of the node.
Oh, sorry.
But basically, yeah, here. But the rest could also, if you have no conflict, you could omit the model name. But basically, it will be like the full path for that is, without shortening, is flow capable flow node inventory. Table. So basically, it says we are going to the nodes node, OpenFlow1 node, and then we are using the extensions from the flow node inventory model, and that extension is table. That's the full path for that.
More or less standard operation. Like the name that we augmentation construct, where you augment one model with another data. And you can actually change your augmentation, which happened here as well. So you've got a full control node, and the statistics are provided by the different component. And that component augments the whole data. And where in the tree can you augment? Can you go all the way to the top underneath config and up?
You could augment on any place in the tree. Basically, that's also with the model driven that we are, and the Yank allows you to augment at any place. And if you were to write, for example, in programming, there is an extensible object pattern. And if you are defining handwritten APIs, there could be places where you forgot to omit the extensible. But now we are enforcing the extensibility on the all levels. So for example, here is that basically we are adding into the inventory nodes node. We are adding the augmentation flow capable node, which uses the flow node definition, which is defined in the same model. And flow node is and the flow node extension defines all these fields like manufacturer, hardware, software, list of then it uses the list of the tables, uses the groups, uses the matters. And if you look closely into the not XML, let's say JSON. JSON is better to showcase this. And if we go to the operational part of the inventory, which is reported, you could see we have a node, which is from the inventory. And then you could see that we have these extensions from the flow node inventory, which is the hardware, which were added by this augmentation, which are the which were defined in the augmentation hardware. For example, there are the tables. You could see that was added by flow node inventory model table, and you have the yet another augmentation for the table, which is the flow statistics. For each table.
This really helps because the development, the flow statistics was developed by somebody else.
And basically,
By doing the augmentation, you need one boundary
yeah, and this code is like, yeah, basically they know where to write in the model, where to write the statistics they gathered, and then they don't need to care how the flow is there populated. They're just writing their extension to the well-known location in the tree. and the other component provides that. And these components maybe not unknowingly, but actually creates extended views. And that's the power also of the model. Well-known locations where the data are stored, and separate components could store the data based on the model and based on their extension on the extensions they provided.
Because they have their own spots in the tree.
We have a common spots in the tree, and they have their own extensions to that spots.
Doing things like vendor extensions comes at a completely different level because you can stick anything anywhere in the tree. Yet, since this is Yang, you have an XML namespace for your module. So even if somebody picks the same name, they have a different namespace, so the data doesn't collide. You always get a full view.
So is that something we should try to do? When we build an application, should we try to do it by extending the model as opposed to keeping it?
Well, yes, that depends what you do. Because there is something already there that is functionality.
So you need absolutely, you use it, yeah.
But if there is nothing, like, for example, in subscribe,
Yeah.
find the model.
And then you get the REST APIs
Absolutely.
for free.
Yes, both in JSON and XML.
Any other questions? Go ahead.
So there's no restrictions on the volume of statistics that you put in the model to collect from the devices?
Could you repeat that?
You could extend the model as much as you want, but then statistics to extend it to as many statistics as you want to gather from the device that it's capable.
Yeah, basically you could extend your model. You could extend with your vendor extensions with type statistics you want to there. You could write your application which are gathering the statistics or do some computation of existing result. For example, the Robert, which is doing the BGP PSAP, he actually has a model which is the BGP RIB. And he's listening on that model. When the BGP RIB changes, he changes the topology model, basically, and rewrites the topology. So you could implement your own extensions to the inventory and to the flow capable node, and you could gather that statistics via your vendor extensions, proprietary extensions, compute them. You are free to do, and you have well-known place. And also with the model, you get an API definition for your extensions. So anyone you want to use your APIs, you will provide with the Java APIs there, and they are able to read your statistics without being connected to your implementation of that model.
So, for example, you want to collect a huge amount of statistics, 100 other statistics from the switch. So you've got a trade-off, of course, of performance related to that. So you could use this standard statistics method that goes every 10 seconds that falls to basis and statistics. You can augment the statistics model with your another 100 stats and write another module, another plugin that goes, say, once in every 30 seconds and collects your extensive set of statistics. And everything else would work just like before. And without doing the code, you can add the functionality of collecting extensive set of statistics at bigger volume. So you don't have to rewrite anything like that. You can reuse all of that.
Probably, maybe outside of the scope of this thing, but it'd be interesting to see like just the flow of, say, a provider, say, plugin versus a consumer, just how that falls from like a model to creating your code, just as an example. I mean, again, that's something for us to compile.
Basically, like playing a lot of them.
Yeah, just to understand. I know some of that's on the wiki.
Yeah, we can actually, take your refinement.
Yeah, that's fun.
I think we run out of the time. Okay. Any other questions?
Talk a little bit about MD-SAL clustering.
Okay. think we ran out of the time. So let's wrap this up. So if you are interested into this demo, you will find it on the wiki. Oh. You will find it on the wiki. Underneath, you put it into the release, Jan?
Yeah.
Find it on the wiki, release hydrogen. Here. Here? Oh. Guys, and documentation. Controller. Here. Okay, here. Creating an MD-SAL plugin application. So basically go to the OpenDaylight Controller Hydrogen Developer Guide MD-SAL app tutorial. This contains pointer to the code, also the explanation of some of the concepts, and basically all what we presented there. Also, if you are interested in the MD-SAL, the other pointer for that is OpenDaylight Controller MD-SAL main page. Which contains also some explanation of concepts and also the reference to all the models available in the OpenDaylight in the hydrogen and description of subsystem which are MD-SAL providing. Okay, thanks for your attention.